Hello everyone. In today's video we're going to be talking about Physics 252 Week 5 Problem 4. In this problem we are asked to use our knowledge of simple harmonic motion to deduce a few things about a vibrating CO2 molecule. So I've gone ahead and drawn what we're looking at in this equation, and I kind of understood this one mode here to just mean that this is one little kind of half cycle of a wave function, if you will, because the first level of harmonic motion is just one little kind of crest, if you will. So here's our little CO2, and it's vibrating. These are not actual bonds, they're just it's going fast, so it has some little motion lines, if you will. So anyways, this is our equilibrium point here, this is our position, and this is our time. So pretty much what this problem is saying is that we are given some kind of amplitude, or we're not given an amplitude, we're tasked with finding an amplitude. So we know that there's going to be some kind of wave-like structure, and just in the way that it's vibrating, it's creating some kind of a wave. So cool. Well, let's go ahead and look at how we would solve this problem. So we're given our effective value here. We're given our energy and frequency. So just based on these givens, we can actually go through our lecture for this week. Actually talks a lot about these equations in detail, but these equations are all from the lecture, and they all relate to everything that we need. So what we're going to do is we're going to use this equation for I believe it's actually for a spring, because normally K is used as the whatever spring coefficient. So in this case, we're using K as in the same way, because a spring on a mass on a spring will also produce a wave, so we can kind of view it the same way. Either way, it's producing simple harmonic motion, so we can use equations relating to simple harmonic motion. But getting into the problem here, just using this first or this last thing, we can solve for the natural frequency here, and again just 2 pi times our frequency, and we're left with this number in radians per second here. So that's cool, but what we can do from here is we can plug right into the equation for the mass, which we're going to use as this right here, and we're going to be saying that this is our effective mass right here, and here's our omega, and here's our K, and just kind of rearranging with Wolfram alpha, we are left with this value here, this 7.24 times 10 to the negative 27 kilograms is our effective mass. And if we think about how this relates to just the mass of a proton, we can kind of say that this is in range with what we would suspect, very small 10 to the negative 27 kilogram type mass. So then moving on, we can use our equation for the energy, the total energy of vibration, which is usually E, and E can be either equivalent to the potential energy or the kinetic energy, total of both. In this case, we're given U, so we can assume that it is the potential energy, and so we can go ahead and plug in to this equation using the energy that we're given as U, and then our K value, and we can solve for the amplitude here, and we're left with 8.19 times 10 to the negative 27 meters. This should say meters, but I hope you guys found this video helpful, and thank you very much for watching.